Okay, in this last lecture, we will revise the time response, chapter number 4. It was a demand from the students. They wanted to revise the concepts from this chapter, so we'll have a quick revision of this chapter. So let's start. First of all, the poles, zeros, and the system response. The output response of a system is sum of two responses. First of all, the forced response and the natural response. We also call the steady state response and the transient response. Whenever we have response of a system, the response of the system is basically because of the transient response. If we have a suppose a system's response and we get something like this and then finally dies to the this portion, if you look at it, this is the transient portion of the response, which is transient temporary, and then this portion is the steady state response, where the steady state has been achieved and it is at a certain value. If we give a step input to a system and we get this type of response, it has two parts. This one is the transient portion of the response, and this is called the steady state portion of the response. There are other two names as well. This is also called the natural response, and this is called the forced response. If you look at the response from another perspective, then this steady state is actually it contains the behavior of the forcing function, the input signal, which is a unit step in this case. So we have constant output at this steady state, and this is the portion where we get the response of the system, which we call natural response. It's because of the nature of the system. That's why it's called natural response. Now we talk about the pole of the transfer function. The poles of the transfer function, as you can see over here, the poles of the transfer function are the values of the Laplace transform variable that cause the transfer function to become infinite, or at any roots of the denominator of the transfer function that are common to the roots of the numerator. What this means is that the poles of the transfer functions are those where the denominator polynomial, that where the denominator of the transfer function becomes 0. As a result, the overall transfer function becomes infinity. So this means mathematically. So this means that it's a special value of s. S is the complex frequency where the transfer function denominator becomes 0 and it becomes infinite. So the transfer function has very importance, a lot of importance in the behavior of the system. It gives us the kind of response that we get, that we will shortly see in the upcoming in a few moments. You will see that. Okay, zeros of the transfer function. Zeros of the transfer function are the values of the Laplace transform that cause the transfer function to become 0, or any roots of the numerator of the transfer function that are common to the roots of the denominator. The zeros of the transfer function satisfy part 1 of this definition. That is just written over here, this thing. For example, the roots of the numerator are the values of the s that make the transfer function 0 and are thus zeros. So zeros of the transfer function are those that make the numerator polynomial equal to 0. Now let's see what this means by considering an example. We'll consider a first order system. We will consider a first order system. The transfer function of this system, has s plus 2 upon s plus 5, s plus 2 upon s plus 5, and we give it a step input. When we give it a step response, this is our g of s. When we give it a step response, then C of S, the response of the system is S plus 2 upon S, S plus 5. This S comes from the step input. So in order to find how its behavior is going to be in the time domain, first what we will do is that we will make a partial fraction expansion like you see here. We don't know A and B, they are unknowns, they are solved over here. We make the partial fraction expansion so that we can take the inverse Laplace transform and convert this response into time domain. So here we are taking the finding the coefficients. We find coefficient A by substituting S equal to 0 in this whole thing. Now what we actually do over here is that first of all multiply this denominator on both sides. Okay, so we will be left only with S plus 2 on the left hand side, and on the right hand side we will have A multiplied with S plus 5 and B will be multiplied with S, because terms the the other terms, this S and S plus 5, when we multiply it with this thing, then this S in the denominator cancels the S in the numerator, so we have A S plus 5 left. And then when it is multiplied with this, S plus 5 cancels out the S plus 5 and we are left with BS. Now we have this thing over with us, and what we do next is that we put S is equal to 0 in that, and that gives us the value of A, because B is multiplied with S and it will become 0. So we will have the value of A equal to 2 by 5, and then when we put S equals to minus 5, then we get the value of B, and B turns out to be 3 by 5. So what you have to do right now is that take a piece of paper and try to do with this working. Multiply both the sides by S plus 5 in this, which is inside this rectangle. Multiply both the sides by S plus 5. On the left hand side we will be left with S plus 2, and on the right side will have A S plus 5 plus B S, and then in that equation put S is equal to 0 and we will get this A. When you will put S is equal to minus 5, we will get this B. So this is, in this way we find the coefficients which you see over here in the partial fraction expansion. Now in the last step, what we have done over here is that we have taken the inverse Laplace transform using the table. So we get 2 by 5. S is a unit step signal. So this equation is actually valid for t greater than 0. Ut is not written over here, but it's understood that it's for t greater than 0. We always take one-sided Laplace transform in control system. So we take the Laplace inverse transform, and then we take the inverse Laplace transform of this thing. We have 3 by 5 e raised to the power minus 5t, as you can see here. This gives us the response of the system. Now what this means? This means that this portion is the transient portion of the response. It will have its maximum value at t is equal to 0, because then e will be e raised to the power minus 5 into 0, that is 1, so we will have 3 by 5. As the time proceeds, this exponent will decrease. This exponential e function will decrease gradually. So eventually, if you put t approaches infinity, this will be e raised to the power minus infinity, that is 0. So this thing will eventually become 0 and we will be left only with this 2 by 5. So 2 by 5 will give us the steady state value. So one thing that we know from this is, mathematically, if we apply limit on this C of t, that limit t approaches infinity, we say that C of t with t approaches infinity, this will give us the steady state value of C of t. We call it CSS. We call it CSS. So steady state value can be obtained from that. So if you look at this again, It has two terms, it has two parts. One is this portion, this is called the transient portion because this is temporary, it will eventually die to zero. It is called the transient response, and this is called the steady state response. When the steady state is achieved as t approaches infinity, this is the steady state of final value. Now, one thing that you should note over here is that mathematically, steady state is achieved when t approaches infinity. But from engineering point of view, we cannot wait for infinity. We cannot wait for time to become infinity. For most of the practical applications, we take t to be equal to 4 times the time constant or 5 times the time constant. Mostly in control systems book, we take t to be equal to 4 times the time constant. For more accurate systems, we take 5 time constants, but as far as this course is concerned, we take 4 time constants, 4 times the time constant of this exponential that you see over here. It has a time constant, and from there is multiplied by 4, and we get a value of time, and we say that this is the value after which we steady state has achieved. And we say that by an approximation, we approximate that after 4 time constants of this exponential, the exponential becomes zero. Actually, it's not zero, but we approximate to zero. So, what's the time constant? If you look at it, e raised to the power minus 5t, then this 5, it's reciprocal. If you compare it with this e raised to the power minus t by tau, this time constant tau is 1 upon 5. So the time constant is 1 upon 5 from this exponential. Now look at this diagram. We were talking about this thing, this response that we calculated for a system. Now here you can see that we have the plant over here. It has a transfer function of s plus 2 upon s plus 5. We are giving a step input to the system, and the output is C of s. And here you can see the pole 0 plot of the plant. We have a 0 at minus 2, and we have a pole at minus 5. So pole is on the left hand side of the omega axis. So as from our previous understanding, we know that the system is supposed to be stable system. We give it a bounded input, the output should remain bounded. Now what is happening next? Now look at this thing. This is the response in time domain 2 by 5 plus 3 by 5 e raised to the power minus 5t, and this is the response in the complex frequency domain, in the S domain. Now what is happening over here is that this pole, you can see the system pole at minus 5, this gives us this portion of the response 3 by 5 s plus 5, this, and when we convert it into time domain, it becomes 3 by 5 e raised to the power minus 5t. So this means that the pole of the transfer function, that is at minus 5, this gives us this portion of the response, which is the transient response, and it is also called the natural response of the system. And it has a contribution from this 0 as well. The value of 3 by 5 is obtained, it is affected by this 0 at minus 2 as well. If you go back and look at this equation over here, we have this thing with us, s plus 2, that actually gives us the 0 of the system. So it is affecting the value of, affecting the value of a capital A and capital B, or the coefficients of partial fraction expansion. So that is determined by this 0. Their magnitude is determined by 0. So this diagram shows that this 0 has effect on both portions of the response, this as well as this, whereas the pole has the effect on this portion of the response, which is the natural or the transient response. Now, where this portion of the response is called the forced response, it is also called the steady state response, and it is because of the forcing function. This is our input signal. 1 upon s unit step Laplace transform of unit step is 1 upon s. So it has effect on the output of the system, the response of the system, and this effect is the forced response of the system. And you can see that 0 has effect on this as well. 0 is affecting both the steady state as well as the transient response. Forced and the natural response both are affected by the 0, and this is what the response of the system is composed of. When we give a step input to the system and we are getting the response of the system, we call it step response, and we have actually dissected the step response and identified which portion of the response is because of what thing, pole and 0, etc. So try to remember this thing. Now here we discuss this example problem, and in this problem we are given a system which is shown over here, and this system has a transfer function of s plus 3 upon s plus 2, s plus 4, s plus 5, and we are giving it a unit step input, and we are interested in finding the response of the system. Now we know that the response of the system would be multiply this r with g of s. C of s is equal to g into r. So when we do it, we have s plus 3 upon s plus 2, s plus 4, s plus 5. And when we try to find the response of the system in the time domain, we have to make the partial fraction expansion. And in the partial fraction expansion, we take these constants k1, k2, k3, k4, k1 upon s plus k2 upon s plus 2, k3 upon s plus 4, k4 upon s plus 5. All these things which are due to the poles of the system, the pole is at -2, -4, and -5, they are called the natural response system. And this one, which has a pole of the forcing function or the input signal, this is called the forced response of the system. So when we take the inverse Laplace transform, this will become the kut or k constant for t greater than 0. We write it t greater than 0. So, and the remaining portion which have the s plus 2, s plus 4, s plus 5, these polynomials in the denominator, when we take the inverse Laplace transform, they become these exponential k2 e raised to the power minus 2t, k3 e raised to the power minus 4t, and k4 e raised to the power minus 5t. These 1 upon 5, 1 upon 4, and 1 upon 2 are the time constants of this. Now, one thing that I want to mention over here is that one of the mode, these are also called the modes. This is a mode, this is a mode, this is a mode. One of the mode is dominating the behavior of the system. What should be that mode? The answer is that the mode that is slowest is going to be dominating. Which time constant would be slowest? We have three time constants, 1 upon 5, 1 upon 4, and 1 upon 2. Which time constant will be the largest? The largest time constant means the slowest mode. Smaller time constant means that it is faster mode. It quickly decays, the exponential quickly decays towards 0. If it has a larger time constant, it slowly decays towards 0. So which one is larger? 1 upon 2 is large or 1 upon 5? Definitely 1 upon 2 is 0.5, it's large, 1 upon 5 is smaller than that. So the mode that is slowest is this one because it has the largest time constant and it is called the dominating. So from this we say that this pole is the dominating pole. It will dominate the response of the system because it is the slowest pole. Those poles which are, when we draw the pole on the complex plane, we have a pole at -2, we have a pole at -4, we have a pole at -5, we have a we have a 0 at -3 over here. The pole that is closest to the j omega axis, which is this one, this one, this is closest to the j omega axis. This one is closest to j omega axis. This is said to be the dominating pole, and you can see that this distance, the reciprocal of this distance gives us the time constant of the that particular mode. If we take the reciprocal of this distance, which is 2 for this pole, that will give us the time constant for this particular mode. This thing is a mode. And then this distance, which is 4, its reciprocal will give us the time constant for this mode. And then for this one. So the largest time constant is for this pole, and therefore this mode, this term of the time domain response will be the slowest term, and it will dominate the behavior. Imagine that we have three some a few children are playing, and there are three kids. One of the kid is very fat and very heavy. The other two kids are quite smart, and they can move very fast. So this the fat kid, if suppose they have to run in form of suppose chain, the fat kid will dominate their speed, because the slower can run fast, but the fatter one cannot run fast. Therefore, he will slow them down. That will dominate the overall speed of that chain. If they are individually running, they will run fast, but when that fat guy comes in, he will dominate the speed of that chain, and he will make them slow. So therefore, that fat guy, that guy with the largest time constant, the guy that is closest to the j omega axis, that will dominate the behavior of the system. So therefore, we say that this is the dominant pole. It will dominate the behavior of the system. The other poles will be slowed down by this because of this slow pole. So this was the solution of this problem. Now our concern over here is to understand the concept of time constant and for a first order system. We will consider first order system for that. So you can see over here in figure 4.4 that we have a system with a transfer function. It's a first order system. Transfer function g of s is a upon s plus a, and we are giving it an input signal r of s, and we are getting an output signal c of s. On the pole 0 plot, you can see that we have a pole at minus a in the complex plane. Now the response of this system is c of s is equal to r times g of s, and you can see that it is a upon s plus a. Then by following the steps that we have already considered, we find the response of the system. First of all, we will make the partial fraction expansion and then take the inverse Laplace transform. Now over here, I suggest that you should take out a piece of paper and try to do the working and get this thing and send it to me and show it to me, that how we get this thing. We have basically made a partial fraction expansion taking, for example, capital A upon S plus capital B upon S plus A, and then we have found the values of the coefficients, and then we took the inverse Laplace transform, and we get this thing. Now this is the response of the system. Now in this exponential, if you look at the exponential, this is the natural response or the transient response, and this one is the forced response. This one is the forced response. This one. Now in this thing, when we put t is equal to 1 upon a, when we take the value of t to be equal to 1 upon a, then this becomes e raised to the power minus 1, and that turns out to be 0.37. And the value of the response c of t at this time when t is equal to 1 upon a, we don't know a yet. A small a is not given, but we say that if t is equal to a, then what happens? Then at that value, this exponential becomes 0.37, and this thing becomes 1 minus 0.37 or 0.63. This is one thing to be noted. When t is equal to 1 upon a, that is such a time where the response becomes 0.63. And the other thing is that When we start our journey, at that time, when t is equal to 0, this thing is whole is 1. So we have 1 minus 1 equals to 0. We start our journey from 0. C of t is equal to 0 for t is equal to 0. At t is equal to 0, C of t function is 0. We start our journey from 0, then it gradually rises, and it becomes 0.63 for t is equal to 1 upon a. And then we proceed forward, and when we apply limit t approaches infinity, and we say that infinite amount of time has passed and t approaches infinity, in that case, when we apply this limit over here, this exponential has e raised to the power minus infinity. Anything raised to the power minus infinity is 0. So at infinity, what happens is that this portion, this term becomes 0, and we are left only with this 1. So the steady state value of c of t is, when we apply c of t with limit t approaches infinity, is 1. So that is one thing. So we started our journey from 0, then we reach this at 40 is equal to 1 upon a, and then it becomes 1 at infinite. So this is what is happening. Now we can generate a table and we can plot it in form of a graph. As you can see over here, what we have done is that we you what as an exercise you can do it right now. You can generate a table. We have c of t, we have this is t, we have t with us. You take t is equal to 0, and then you make it 1 upon a, then in terms of 1 upon 2 upon a, 3 upon a, 4 upon a, 5 upon so on. And here we get the values of c of t. So generate a table and put the different values of t in terms of a. T is equal to 1 upon a, t is equal to 2 upon a, 3 upon a, so on, and plot a graph. Now in this graph, this is going to be the waveform based on the numerical values that we obtain from the function that we have found for c of t. So this is the shape that it initially it rises very sharply, and then gradually it becomes slow, decreases, and finally at it becomes flat. So this is what is happening. Now in this, there is one thing that is important. The rate of rise is largest, highest at this point. The slope is steepest at this point, t is equal to 0, and it is 0 at infinity, flat over here. And if 5 1 is finite, it's close to 0 but not exactly 0, and it becomes 0 at infinity. The slope becomes 0. How do we get slope of a function? What we can do is that, what you should as an exercise do is that, differentiate this function and we'll get the slope of c of t. If we differentiate it, 1 becomes 0. The exponential, as far as exponential is concerned, it becomes minus sign is cancelled by the minus 80, minus a e raised to the power minus 80. So the minus sign of exponent, the power, that cancels out this minus sign, and this becomes positive. So slope is positive, and the slope is a e raised to the power minus 80. When we differentiate it, the slope is a e raised to the power minus 80, and the maximum value of this is for t is equal to 0. When t is equal to 0, then e will become e raised to the power minus 0, or it will become 1, and the slope will be a. The maximum value of the slope would be a. As you can see over here, the initial slope, maximum value of slope is for t is equal to 0, and that turns out to be a. If suppose the response is allowed to rise, which does not happen, if it is allowed to rise with same rate of rise, it will reach the steady state value. That is, the steady state value is this one. Steady state, we have already calculated the steady state. It will cut this one line at a time that is equal to 1 upon a. So we define this thing as a time constant. Time constant is that time, if the response is allowed to rise with its maximum initial rate of increase, then that response will cut the steady state value at that time. And Actually, what would be the actual value? The actual value would be, it is the time. It is the time where the value C of t is 63% of the final value. Actual value of C of t would be 63% of the final value at time constant. So we define the time constant as a time where the response of the system would be 63% of its final value. And we can define it in another way, that it is a time if we allow the exponential response to rise with its initial maximum rate of increase, maximum slope. It will cut the steady state value line. It will reach the steady state value in that amount of time. That time is called the time constant. That is 1 upon a over here. So we can define the time constant in both ways. It's basically a benchmark. It's a way to measure how fast or how slow a response is. We can have different time constants for different functions, different exponentials. So we measure the speed of response of a this type of signal with by using the concept of time constant. Exponentials have time constants. Time constant, like I've said, if it is has a larger value, then the signal will be slower to move towards steady state value. If it has smaller value, it will quickly move towards steady state value, and so on and so forth. So that was the concept of time constant. Now we'll talk about the response of second order systems. We have the transfer function of a general second order system in this form: b upon s square plus as plus b, and we give it a step input, and we get the response of system. And what's going to be the shape of the response, we will be talking about that. So if you look over here and we focus on the first type of system, in this system, if you look at it, this is the denominator polynomial is s square plus 9s plus 1 plus 9. This system has, if you find out the roots of this denominator polynomial, the root turn out to be this and this. Okay, so we have two real negative roots. Both of the poles, these are the poles of the system. Both of the poles are negative. They are real. They don't have imaginary part. They are real numbers and they are negative numbers. So this type of system will have a response of this shape. If we make its partial fraction expansion and we solve it, then after for we even have numerical values over here. So this will be the type of the response it has. It's an overdamped system because the both of the poles have only real part, and it's a stable system. We give it a bounded input, and the output remains bounded. Both of the real system poles are real, and they have negative real part. Now, when we have a situation like this, as you can see over here, s square plus 2s plus, when we take out the roots of the denominator polynomial, the the roots of the denominator polynomial turn out to be minus 1 plus j minus 1 minus j under root 8, minus 1 plus j under root 8, and minus 1 minus j under root 8. These are the two poles which are complex numbers. They have a real part that is negative and that is equal to minus 1, and have an imaginary part as well, and that is j8 and minus j8. And that is the situation, and we may try to make partial fraction expansion and solve it, then it will give us this type of response over here, which you can see. It has an overshoot, undershoot, and oscillation. Whenever we have the imaginary part, that system response will have oscillation, because this thing corresponds to omega. We have, this is j omega axis, so omega is we have the value of omega under root 8. Whenever we have this kind of situation, this means that there is some oscillation. Omega is not zero, there is some oscillation in the system response. That is what is seen over here. We have this oscillation, it goes up and down, this oscillation, and then finally eventually it decays to zero. Then this minus 1 shows that there is an exponential envelope over this response, like this. So the peaks are exponentially decreasing gradually with the passage of time, and eventually the system decays to zero at t approaches infinity, and we take the that time to be settling time. We call that settling time, but we take settling time to be 4 time constants. 4 time constants of this exponential envelope. We have this exponential envelope, it has certain time constant. We multiplied 4 with 4, and that gives us the time constant of the system, and that gives us the settling time of the system. That is the time after which we say that the system has reached the steady state value. So this is the behavior of the underdamped system, where we have the poles in this way, which are complex numbers. They have a negative real part and they have a non-zero imaginary part as well. Now we move to this system. Here you can see that this one term of 1 power of s is missing. So this is the case where the poles are on the j omega axis, under root 3 and minus j under root 3. Sorry, j3 and minus j3. There is no real part is 0. Real part, and the one thing that you should notice, that a real part and that is negative means that there is an exponentially decreasing envelope. The response will eventually decrease to 0. If it is a positive part, then it would be an increasing exponential and the response will increase, and that is the case of unstable system. We give it bounded input and the output becomes unbounded. That is that case. So here we don't have the case of unstable system, we have the case of stable system. For stability, the real part should be negative. So whenever the real part is negative, we have a stable system. Now here the real part is 0. When the real part is 0, this means that there is a straight line. This means that there is a straight line like this and this on the peak. It is neither increasing with time, neither decreasing with time, and we have non-zero G omega. Omega is non-zero, therefore it oscillates. So we have an oscillation over here, and the peaks are not increasing with the time and they are not decreasing with the time. So we have a case of sustained oscillation. So we call this undamped system. Normally we don't have such cases in real world because there is some sort of damping. And undamped system means that once energy is put into the system, it will remain inside it forever. In the real world, the energy goes out, there is friction, there is drag, there is resistance, etc. So there is damping, but this is the case of undamped system. And although this system gives you a bounded output for a bounded input, but if you give it an input signal that has a pole at with the value of this 3, then what will happen is that the response will become unbounded. So therefore, this is a marginally stable system. It's not a stable system. It is not unstable. It's marginally stable system. Marginally stable systems have a property of giving unbounded input when the input is bounded, but it has a pole that corresponds to their pole mm, uh, on the geometric axis. Now we have the critically damped system. A critically damped system is one which has two equal poles. As you can see over here, the poles are at -3, and for that this is the mathematical expression and the graphical representation of the responsive system. It's a critically damped system, and the damping ratio zeta is 1 in this case. 2, we have 2 zeta omega n over here. Omega n, this is omega n square, which is 9, which means that omega n is 3. So we have 2 into 3 equals to 6. This means that zeta must be equal to 1. So we have a critically damped system where the zeta is equal to 1. Now here this is another important figure that must be considered for a second order system's response. And you can see that if the system is undamped, we have sustained oscillations. This is shown by this sinusoid. When the system is underdamped, we have an overshoot and undershoot, a damped oscillation. When the system is critically damped, there is no oscillation, but it reaches the steady state value like this. And an overdamped system is slower response. It rises slowly and then moves towards the steady state value. So these are the different types of response that we have for a stable second order system when we give it a step input. We have the transfer function over here of a second order system. In this If you compare it with this general form over here, you compare it with this form b upon s square plus as plus b, and we compare it with this form, then we say that this omega n square is b and 2 zeta omega n is a over there. What is omega n? Omega n is the undamped natural frequency of the system. If you make the middle term, that is, if we make somehow make this 0, we have omega n square upon s square plus omega n square. The poles would be on the j omega axis at j omega n and minus j omega n. So that gives us the undamped natural frequency of the system. If there is no damping, it will oscillate with that certain frequency omega n radians per second. Now this is 2 zeta omega n. What is zeta? Zeta is the damping ratio. It's a unitless damping ratio. It gives us the information that how much damping is taking place. What is the rate? If there is more damping, the system will be, response will be overdamped. Energy will eventually will come out of the system quickly. If it is under-damped system, there is less damping, then the energy will remain in the system for a longer period of time, making it oscillate. We have the overshoot and undershoot and oscillations in under-damped system. If the damping is zero, this means that energy will not leave the system. Theoretically, if it goes into the system in form of some step signal, then it will remain inside the system forever and it will keep on oscillating because of that energy. So that is the concept of damping. Now, if we try to find out the roots of the denominator polynomial, the roots that we obtain from this are minus, as you can see over here, minus zeta omega n plus minus omega n zeta square minus 1. Now, if zeta is greater than 1, this thing is the way it is shown over here. If zeta is less than 1, in that case, this will become complex imaginary part. This will become imaginary part, and this whole this will become complex number. So when we have zeta is equal to 0, from this, keep this thing in view. When zeta is 0, in that case, this is the undamped response, and the poles are on the j omega axis, and we have this type of response: sustained oscillations, undamped oscillations. When zeta is between 0 and 1, in that case, this thing becomes we have basically zeta is less than 1, and when we subtract zetas from zeta square, we subtract 1, then this means that we have a negative sign, negative number under root. Therefore, this becomes imaginary, and we take that minus under root minus 1 as j, and the poles that we have, they become complex numbers. So when zeta is between 0 and 1, the poles are complex numbers, and we get this thing. And this is the response of a underdamped system. Whenever we have this imaginary part where we have omega n under root 1 minus zeta square, we call this damped frequency. It gives us a damped frequency. Omega n is undamped natural frequency. Omega n under root 1 minus zeta square is called damped frequency. So with this damped frequency, it will oscillate and eventually die to 0. When we have zeta is equal to 1, as you can see in this case, both poles are same location and they are real and negative, then in that case we get the critically damped system response as shown over here. And when we have the poles that are in such a way that zeta is greater than 1, then this corresponds to overdamping. There is too much damping. In that case, we get the poles like this, real poles, but unequal poles. And when we try to solve it, one of the poles is, you can see that this is minus zeta omega n plus omega n under root zeta square minus 1. Zeta is greater than 1, so there is no problem in under root. There will be no negative sign under root. And this is one pole, and this is the other, this one pole. So when we have this kind of system, we have an overdamped response. Overdamped response is slower as compared to critically damped system. If you superimpose these two graphs on the same graph, then The overdamped system will be something like this, slower than the critically damped system. Underdamped system will be overdamped system will be slower than the critically damped system. Now the underdamped system is concerned, then underdamped system will be have will rise faster, but it will also overshoot and undershoot and finally decay to zero. So the position of the poles, the value of the zeta, value of the omega, and they determine how what is going to be the shape of the response when you give it some input signal. And in this case, we are considering the step response of the system, and the input signal is a step signal.